Let me just add something I had forgotten to ask for the last 2 weeks, that one of you had lost your homework and it didn't show up in my graders. Likely it got stuck, staples get interlocked a lot, it's going to happen on your test, so you can fight with another person over your test because it got interlocked. So the thing what happened was, this person's homework probably got locked into someone else's homework, and then it just went through the grader and got returned to you. So if you folks could check whether one of your homeworks is locked in with the staples interlocking to this person's homework, because we've lost it. And well, anyway, so if you could just do that for me. This does happen a couple of times, by the way, when some of you go to pick up a homework. Often when you pick up a homework, you take your homework, but you accidentally take someone else's. That happens a lot, and that person can't find it, and we have their grade. So anyway, look for that. Let's see, all right, I've got, again, quite a bit of notes on how to do derivations, which will be on the next homework, which will be a large part of the next test. I also brought a copy of the test. I circled questions that are where the funny parts to find answers, parts to understand how I write these. And I don't mean to be a weirdo, it's just I am a weirdo, and they asked me to write them, so I did. So I'm just all you got, sorry. Let me get the doors. I brought candy, and let me tell you folks, after I did all the grading, I was kind of tempted to give everyone a D, because you took candy from a stranger. I just want to point that out. So, tell you what, my plan is to go over the questions, the derivational type questions. They're kind of neat. They're I think a little bit on the fun side if the derivation can be fun, and then go over the test because you have the answer key. Then at the end of class, return the test. Now remember, when it comes to get the test. No, I got that one right. You think you got it right? Okay. Please check the answer key. You're just saving us both a lot of time. And it's not going to bother me. And of course, as you notice, as you turned in your test, this is how I learned your name. I looked at the name as you handed to me. So I know who you are now. So again, please just look at the answer key before you want to ask for a regrade. On the same time, note that I know we made a ton of mistakes. Like when I was adding up the scores, I had trouble reading one of the numbers. And so I thought, well, I'll add it up again. It looked like it's 6, but I wasn't sure. One of the questions was 6, and above it, a question was scored at 10. It was 16, not 6. And had I just had some trouble reading that 6, I would have added 6, not 16. Not because I'm trying to be a jerk, it's just we make mistakes. So double check, I know we make mistakes. Come by office hours to have them fixed. Don't worry about the TAs. I'll fix them. I know there's mistakes, so get it fixed and come by office hours and let me change your grade. I won't do it any other time because I want you to watch me change the grade book. If you come up to me and say, oh, I clearly deserve another 5 points, and I look at it and say, yeah, I guess so. You know, I go up there, yeah, that's gone. It ain't going to happen. I'm not going to change the grade. Not because I don't want to, it's just I'm going to forget because something else is waiting for me at my door that's going to distract me. So just a caveat. Again, I want you to get all the points you deserve. And don't let, folks, there have been plenty of times that a single point would have changed someone's grade. So don't be slack on it. Don't say, man, it's only a point. Well, that 1 point can change your grade. And I want to give you that point. I don't care. So, I mean, it just points to me. I mean, whatever. Questions? Should I be more questions? Okay. Can I have a piece of candy?
Can I have
yes.
Are CP and CV equal for solids and liquids?
CP and CV equals for solids and liquids? I'm actually not too sure. So, you know, CP and CV are very different for gases. My guess is they would be, but here's a neat thing. And I'll actually help you answer one of the questions on the homework. CVs for a lot of solid state materials, liquids and solids. Liquid is technically a solid state material because it's not a gas. The CVs are not known. Because how are you going to calculate the CV of iron? You have to heat it and not let it expand. What are you going to do? Put it in a piece of iron? That ain't going to work. Put it in a piece of diamond? So CPs are known for solids and liquids, but it's fairly limited because you actually really don't have a good way of keeping them at constant volume. When you heat solids and liquids, they want to expand, and the force of that expansion is very strong. So we have taken the time to build really strong cells and put things like water in them, liquid water, to get CVs and CPs. And I think they actually aren't very different because they don't expand much. So, but for the most part, the CVs aren't known. So, okay, other questions? I'm sorry, now I'm going to help you on your homework. Now, remember that when it comes to temperature, delta S. I told you this once. I almost screwed up, I almost put delta T. Okay, now remember that you have, when it comes to temperature change, you have to know whether you're at constant volume or constant pressure. Now, I have a question on the homework about the entropy change of a car engine, and I actually looked up the real numbers. I looked up the weight of a car engine block, which is about 150 pounds, universally made of iron, although there's a move to make them out of aluminum, but they're mostly made of iron. And you have to calculate the entropy generated from going from room temperature to 90 degrees, which is the temperature change that happens as you heat up your car. Again, I'm trying to give you real numbers, so it's more meaningful. That car is at constant pressure, right? So you need to use CP. But now when it comes to all the gas expands and gas contracts, you're going to use CV. And that's because when you're doing these transitions, it's like the question on change in U. You can let volume change and then calculate entropy NR ln CF. So this would be an 80, let's do an adiabatic irreversible change in S. Because of the path independence of S is the same as U, I would actually do it this way when it comes to gas in the box, because I can, in my mind, let volume change and keep temperature constant, and then I keep volume constant and let temperature change. It didn't actually happen, but it doesn't actually matter. So on the homework, you have a question where you're going to use CP, this, CP LNTF over TI, CP, because it's a constant pressure question. You'll never see that again. I just want you to know that that's how it works, but I also want to simplify this class as much as possible. From now on, aside from that question, everything will be a CV, because it's all going to be gas in a box. Anyway, I just want to throw that out there. There was another question? We're okay? I'll have to okay, all right, well, I'll tell you what, we're going to have a gazillion derivations. Let's start off. So, to keep this class fun, I often think of things like this here. I mean, if I'm not having fun, then it's just like, entropy is a function of volume. You know, that would really suck. So I want to keep myself entertained so that, you know, I don't do this stuff. And what happened was, 3 years ago, someone said, okay, dP dt is nR over V. And I said, that's right. He said, so that's for isothermal this and that. And I'm like, yeah. He said, does it work for adiabatic conditions? And I looked at it and I said, I don't know, maybe, I guess so. That's wrong. And so 3 years ago, this isn't in your book, but it will be on your homework and on your test, I started figuring out dP dV and constant S, not constant T, right? Isothermal versus adiabatic, adiabatic reversible. So when it comes to adiabatic reversible, the whole dP dt, dP dV, dV dt, all the combinations I can come with at constant S, because adiabatic reversible has entropy constant. The relationships, by the way, also work for adiabatic irreversible, but let's not worry about that so much. I realized that you can't use the perfect gas law, right? You can't use the perfect gas law for dP dt, which is nR over V, that's for isothermal. And again, you can't do that for adiabatic. You cannot do that because T is then changing. Remember, you can't talk about dP dt when V is also changing. You have three partials, not two. And if I have three partials, I'm kind of stuck. I can't deal with three partials, right? Because either things have to be, you have to divide partials to get derivatives, or they have to be integrated. You can't do both simultaneously. So with three partials, you're stuck. So that means you have to do things a very different way, and then you get good answers. Okay, let's do them all. PDV and constant S. Again, this will be an adiabatic reversible. And adiabatic reversible represents perfection. This is the perfect engine because Carnot was adiabatic because it was wrapped in glass wool, and it was reversible because the total entropy change was 0. And we know that's a perfect engine. Now, unfortunately, this is, like in so many things, it's painful. I'm going to do one derivation, I then do another derivation, and then I add them together. And that kind of blows, but it's going to get to these. Okay, the way to start this one, I've worked through them many times, so I know what the right starting points are. is I'm going to do the U is TDS minus PDB. Okay, so one person said, hey, wait a minute, now, tell us a little bit more about how do you know where to start these? For one, I've worked, whenever I ask you any of this, you're going to want to start with the function of energy. You're going to start with the function of energy, and you slowly have to tease this out, if not tease it out directly. Now, as you can see here, I have a change in V, I have a change in V. That's why it's a good starting point. I'm keeping S constant, I have a change in S. All right, so this is good. This is good. I'm going to wipe out this term, right? I'm clearly going to wipe this term out. That's why I want to have S, a change in S. Not S, but a change in S. I'm going to have a change in V. So I want a change in V in there somewhere. That makes it easy, because I'm going to end up with a minus T. But I don't have a change in T. There's no change in T. Nice. So that kind of sucks. That means that the derivation is going to be a little bit harder. Okay, so what I've got this now. What should I divide by? Delta D and hold what? Right. Right, because that wipes this term out. Oh, sorry. Oops. So what I was about to do. Okay, obviously that wipes this out. And this is 1. Okay, just write that a little bit better. Okay, so I simplified this in a nice way, but it's not exactly helpful yet. Okay, now I can also do this. Now, that's one derivation. Let's do the next derivation, and we add them together. Okay, now I am adiabatic reversible. Tell me what to do when I have adiabatic reversible. What's the change in U?
Negative PDB.
Negative, no. Remember that, okay, adiabatic. We always get to the change in T. Change in T is paramount. You calculate the change in T, you get everything else. Now that I've got the change in T, the change in U is CVDT. Right, CVDT. Okay, now what I'm going to do is divide by change in V, the constant S. Now it can tell me what this is equal to. See, now I found the guy I'm looking for, but what's this equal to?
Negative P.
Right, negative P is right up here. T, V, constant S is minus P over CV. There you go. Now that's something I can work with. Okay, now tell me, if volume increases, what does temperature do? Decrease or increase? All right, if V goes up, T goes down. Why? Negative. Pressures are always positive. There's no such thing as a negative heat capacity. That's like a black hole. Actually, I think the cements of black holes do have negative CVs. But so this is all positive, but I have a minus sign, so it's all negatives. So if V goes up, T goes down. So tell me something. When I adiabatically expand, what happens to the gas? Gas cools? Right, the gas cools. You already knew that. You see, you got the right answer. And if we did this, at constant P, see, I don't have an analogy. So this would be the isothermal case. This would be P over NR. Right? Yeah, T is PV over NR, so I just get rid of the V. All right, so notice that, and this applies to the isothermal case. So remember, isothermal, I can use PV equals nRT for anything, because only two things change. A change in V results in a change in T. But here, if I'm changing V and T, I'm also changing P. Right? That's how the whole process began to begin with. So I can't use P equals nRT. Look, the sign's changed. So when you're doing adiabatic, a lot of things reverse themselves. So, and maybe they'll even write that down and scratch that down. I don't want you to get confused. But anyway, look, I'm going to be asking questions on this on homeworks. The next homework, you're going to have a lot of these guys. I'm going to do them all. You're going to have a lot of these guys, and this is how you'll do them. And I'll ask you to prove that they're correct as well. There's my notes. So now these will be definitely in the Life and Universe and Everything section.
Question.
Uh-huh.
At that point, when you have the starting point, why don't you just divide by delta t and then get there without like two derivations?
Wait here?
Yeah. So why don't we just do divide by delta t, because we already have delta v. So if you divide by delta t, that would get there faster without.
And hold,
We won't need two derivations in that case.
let's see, there's always more than one way to do it. Let's try it. I don't know, I've never tried it that way. Let's see what happens. You said divide by delta v,
Yes.
and then hold s constant, right?
That way.
What is that?
Delta t.
I know, I just talking to myself. Okay, that's gone. I don't know what to do with that.
That would turn into CV, right?
Has to be
So that would turn into CV?
Probably does,
Does, but we don't know that, right?
but I don't
So
know
we
why.
can.
No, it's a good, this is a way to do it, it's just I have to turn that, I have to figure out that this is equal to du to the t a constant v. That's what I'm gonna do when I go home tonight, because I don't do much. Figure out what du dt a constant s is du dt a constant v, and I'm gonna play with my cats. I got it. It's a good idea, it's a good idea. So that's, if you go this route, that's the sticky wicket. And here, this route was that I just didn't have this, I didn't have this, so I had to do two derivations. Here, you are also stuck with two derivations, you just gotta do du dt ds's. Right, so you probably did an equivalent derivation, it's just that you still end up doing two steps. But that was a very good idea.
But at least you'd know what that derivation would be for that one. You have to figure out what the second derivation is going to be.
Well, I know, it took me a while. Look, of course, remember, I always start you out. It took me a long time to figure this out. I don't expect you to do it, and if I do, it's because I've done it now. No, I'm just kidding. I'll give you starting points, I'll give you hints, and I may ask you to prove it's correct. There's lots of questions. I'm going to give you a couple examples. Okay, let's say that I give you, come on, you guys are a little nutty to me, all right? So let's say I give you this. So this is the kind of question I'm much more likely to ask. If I do ask you to do one of these, then I'll give you more than enough hints to start you out. But here's a question I definitely can ask: is this correct? All right. So it's going to be t is minus p over cv dv. And again, that's me manipulating partials like fractions, which is completely calculatable, it's fine. Okay, now, remember, I'm obviously setting myself up for an integral because I have partials by themselves. Partials by themselves must be integrated, and right now, I've got 0 equals 0. I've got the change in volume, but pressure has volume in it. I have to bring that out. So that's nr. Okay, next step.
What happened to your V?
I'm missing a V. Right. nRT over V. I'm missing a minus sign, and this is a minus sign. Right, sorry. Yeah, sorry. I'm doing this off the top of my head. So I'm going to screw up. Integrate. And what I've got is natural log.
You're still missing a V.
Yeah, I'm sorry. Am I missing a minus sign?
Yes.
Look, I got it. And I can already tell. I don't even have to think about it. Because I've already done this derivation, I'm not going to work at all. And hopefully this is correct. There you go. The adiabatic equation of state, which I derived by other means. So again, is this correct? The way to prove it, which I would tell you to do in a homework or test, is to show me that it returns to the adiabatic equation of state, which I derived by other means, yet I get the same answer. So this absolutely has to be correct, no doubt about it. Sorry, but I'm doing these on my own. I haven't made as many mistakes as you will, so, because I'm just as likely to forget, so, PhD or not, I'm just as likely to forget a minus sign as anybody is. So, what I do is I check after the fact. I just don't have that luxury right now. So I'll screw these up a lot, but anyway.
Sorry.
There's TV on that thing? All right. Okay, so now remember, I've got a potpourri of letters. Let's do another one. Let's do the HDD and constants. Okay, now let me tell you a little bit more about what I'm looking for in these. When it comes to all of these, what I want you to do is get the thing equal to things that I know. Like in this case, I know pressure is positive. There's no negative pressures. I know heat capacities are positive. There's no negative heat capacities. There's no ambiguity that two positives with the minus sign is a negative. That's a stopping point. And if I had to do transformations like to prove it, like to turn the P into nRT over V, well, so be it. But that comes later. All right, so that's really what I'm looking for. So where am I at? Sorry. Now, as you can imagine, what's my starting point? Now, this one's obvious. H. Right, of course. You're going to start with change in H. This is the one that's all positive. GDP plus TDS. That's right. So you just those two times. And then, as you can imagine, I'm just going to go straight there. I do believe this is still a two-step. Is this still a two-step problem?
Yes.
I'm kind of doing this wrong, actually. No, I started off in the wrong spot. Because again, I'm on autopilot. Yeah, I'm on autopilot. Sorry about that. Let me back up. Sorry about this, folks. I screw up sometimes myself. Yeah, it's change in H, but what I actually want to do is in this form. You see, this is why, again, I'm not going to leave you out on your own when it comes to doing these, because the way I was going was going to be very difficult, and I know that because I tried it. It took me several steps, but I found if I did it this way, it's just a handful of steps. You always will get to the same, you'll always get to the right answer. It's just how hard is it? And I know because I worked them all, and I'm giving you the easiest one. So again, you saw me go on autopilot and make a bad choice. Okay, now, again, now why this is kind of nice is that the change, because we're adiabatic reversible, what's the change in U? CVDT. And like a lot of you did on the question, you did this. On the last question, and which I'll go over in a second, a lot of you found another way to derive the last question on the final, the first test, that I never thought of. You did it this way. And I never thought of that. That's clever, but I'll go over that as well. I've got plenty of time still. So, okay, so let's go for the jugular. Is that right? Yeah. Okay, so, yeah, there we go. All right, see, the thing is, another hardship about these is that I'm doing these in a certain order because you see, what is this? The TDD of constant S?
Negative P over CV.
Minus P over CV, I just did it. So I found that when I was doing all these derivations, again, this took me a couple days to work through all this. You need to do them in a certain order because they build up on top of each other. And again, I'm doing this because this is the fastest way. Okay, minus P over CV is minus P plus NR. Minus NR because of the minus P over CV. you go. Now, what I found was that, okay, this is the test. You write this, you stop. You're done. Remember, people used to simplify things because they had no calculator. They had no calculators, they had no computers, they had slide rules. Simplification made things a lot easier. You don't need that. Remember, your calculator has more computing power than the lunar lander in '69 when Neil Armstrong landed on the moon. That thing is more powerful than that. And so there's no need to simplify things anymore. Computers are more than powerful. But they weren't. It really was a big problem back in the day. But let me simplify it for reasons you'll see in a minute. So minus PCD. And I'm always amazed how just multiplying by 1 makes everything easier. Okay, now I've got, what do I want? Minus P. I'm going to do a couple steps of algebra. CD plus NR. Oop, that's awful. Over CD. It's minus P, CP over CD. H, dV, constant S. Did you do that right? Yeah, okay. Yeah, there you go. Okay, if volume goes up, H goes down. Okay, now that's all fine and good, but is there a little bit more fundamental there? Yes, I can now answer the question, but why does it make sense? Okay, if volume goes up, what also goes down? Okay, pick another one. Temperature goes down. Right. Now, we know that U is a function of temperature through the equal partition theorem. If temperature goes down, then internal energy goes down. So H should go down, unless it's balanced by this. But this is NR change in T, and temperature went down. This goes down, and nRT goes down, because temperature went down. Temperature went down because volume went up. Temperature went down, so enthalpy went down. Am I a liquid or am I not? So, anyway, I just want to point out that we can answer the crude questions of, yes, that goes up, that goes down, but we can also kind of see why. Because temperature went down, and remember, when you're doing adiabatic, remember that temperature was everything, especially for enthalpy, because you got U, and then you got nRT. Right, and so there you go. Everything always depends on temperature. Okay. Do another one. Right, this can go on forever. I got P and V now. Yeah, I got P and V, and that's all of them. Then I've got, then I'm going to do U and P and U and V, and all that jazz. And just a couple more. Come on, folks. This is a little out of control today. Like my cat, I bought a catnip last night. It's pretty freaking nuts. It was hilarious. Frothing at the mouth. Why don't you start smoking from her ears? Okay, so this is the question. What's dP dV at constant S? All right, we've done all the other combinations, and remember, I could come up with combinations. I could ask for dV dP at constant S, but then I just flip the present result. All right, so this is all pretty simple. Okay, now, guess.
H.
Yes, H, because I have pressure. And let me make sure I'm good. Okay, this is one of those times we're going to want to do it right. PDS, not the other form. I kind of just choked on my computer. I know that. Okay, we go straight for the jugular here, dV. Right, because I have a change in P, I got a change in P, that says I wanted H, and I'm going to hold entropy constant, so that meant I wanted a change in S as well. That meant not go for G. G would have a change in P, but a change in T. And that makes this not, that's going to take a long time, it's going to be hard. So I wanted to change in S because I know that I can now kill this term. dV, okay, constant S. Oh, wait a minute, we already, yeah, okay, so I'm trying to get to this. Now, I'm really one step away. Now, remember these build up on each other? It's right up here. Sorry, my notes, where am I? on the wrong page, is the problem. Okay, minus P, CP over CD. And then I'm going to bring over 1 over V. CP, V. Okay. Okay, if volume goes up, then pressure goes down. Okay, that's just blindingly obvious. Now let's do the usual, is it right? Okay, with minus CP over CD, PV over V is the change in pressure. I'm sorry, so you understand that we're going down a different route. Okay, there's that. Integrate both sides. And what I'm going to do is eat the minus sign. I'm going to do 2 steps of algebra at once. I'm going to have not VF over VI, I'm going to have VI over VF. Why? Because of that minus sign. I just ate the minus sign. And I hope that you're up on your basic algebra and calculus, that this isn't a problem. Okay, I mean, I hope this really doesn't take you but a bad of an eye to see how this goes from here to here. Just properties of natural logs, raising this up here, flipping that because of the negative. And therefore, then I have the obvious result. CI is VI over VF is CP over CP. CP over CP. Right. And by the way, in the handout where I worked several of the adiabatic equations, when I started out with this guy, or the variance of, I mean, I can flip these and have this over here, which is what I did. It doesn't matter. When I worked several other ones, like you did on the test, this is actually one of them, so this is correct. So there you go. Again, it's just more examples of questions I might ask. And the more I do these, the better off you are, because I'm going to ask them. Okay, let's do another one, dV/dt. Do dV/dt at constant S. I'm sorry, I haven't done that one. I didn't put D and D. I thought I'd done them all. And then I've got one more after that, and then I can go over some test questions. Looks like I didn't give myself a lot of time, because these are kind of hard to explain. Okay. Okay, again, U, H, G, or A? U, right, because of the volume. Good choice. Now, again, I will make sure that you start out right. And you want to do this the way okay, 2 tricks. And of course, I should just go ahead and do. Oh, look at that. I'm wondering if I'm answering that previous question. Anyway, I'm going to work that out. Okay, that's obviously 0. That's why I do it. Okay. And here, what did I got to do now? I'm a little bit lost at this point. Okay. The way to do this is another derivation. Changing U. As usual, again, adiabatic reversible. I had to think about this for a second. Adiabatic reversible. dV/dt. Oh, hey. Your question here looks like I'm actually answering it. Okay, this goes away. Is that right? Yeah, so all of this is equal to CV. Okay. In which case I've got dV/dt. dV/dt is my dV over P. Is that right? Yeah. Yeah, that leads to one more example that I have, and then I think I pretty much pretty much done with that. Yeah, then I'm pretty much done with that, I can go over homework. So, okay, again, temperature goes up, volume goes, right, so when you compress a gas, basically it gets hot, right, exactly, so you proved it again. Now, the last bit on my notes is, oh hell, let me just do one more. Sorry, you see you guys struggle with these, so I'm kind of lost there for a second. Let me give one more and stop there. Anyway, so just remember, when it comes to the next week, it's going to be blah, blah, constant blah. And I'm just going to work them and work them and work them. Lots of homework questions, and then 2 will be on the test. Probably one of the derivation questions will be exactly the blah, blah, blah. And definitely that will be one of the derivation questions, but I may ask one that we've already done because I'm going to get confused because I've given so many examples. But then you're going to be so used to it, it doesn't matter whether you know it or not. It's going to be constant gas. And, okay, so that's changing that's the question, so you know. And when you write the U is PBS, PV. And you get VP. Again, this is always the trivial. And let's see, what have I got? I just did the VDP. Actually, we did that one. On the side, we did this. I just I don't. Do I have it up here?
Yeah, left corner.
Yeah, I have it up there. Okay. Now, I've done the PVD, not the VDP. So what do I do?
Flip it.
Just flip it. So V, CV, CP, no. See, why did it? CP's on top. Sorry about that. Here, let me just wipe it out. Sorry. Sorry being an idiot. Minus P times that. What over that? VCV. PCV. Okay. All right, there's a negative, right? I pick up a negative from the VDP. There's a negative, right? Okay, so if pressure goes up, U goes up. If pressure goes up, what else goes up? Again, gas, I have to compress the gas. If temperature goes up, equipartition says that U is a function of temperature. If temperature goes up, U goes up, and sure enough, it does. So there's roundabout explanations to all of these. That kind of makes sense. And again, I can bring the P over here, and we can do derivations that correspond to other works we've done, and it all makes sense. So I've got 5 minutes left. I'd like to go over the tests, show you a couple of pointers that I had. If you want to leave, just do it really freaking quietly. And let me start. Any questions? Are you okay? No questions? Okay, well, let me point out a couple of hints on the test. Okay, I'll toss this up here. I haven't been doing that, have I? I'm going to screw that up. I should rotate this. Okay, again, if you want to squirm out, that's fine. Just be quiet. Because I think a lot of people like to see some hints on the test. Now, again, I'm not getting out the test, so I know a little in one moment. But true and false. Number 1. So watch the video, and you can then look at your test at the same time. Okay, hold on. All right, everyone. SI. So the first one, SI, is liter for volume, and B, J meter squared over Newton. Okay, now here's what's actually happening. For one, there are plenty of you who just said part A is right, part B is right, part C is right. I mean, I told you not to do that 10 times. You lost a tremendous amount of points on that. Tell me which one was wrong. Is this one? Notice that I'm trying to jog your memory. The one that's right will help you figure out the one that's wrong. I do this constantly. That was true on most of them. I'm putting this in your face. Meters cubed. I'm trying to get you to remember by seeing meters cubed that means that the SI is not a liter. I'm trying to elicit that from you and get you to recall your memory simply by seeing it. So that's another tactic I have to use on these tests. Also, a meter squared over Newton is pressure. Guys, really, come on. All right, so a meter squared over Newton, this is joules over pressure. Right, and that should be volume, right? Because pressure times volume is a joule. So anyway, this was correct, but just look out for that. Okay, part B. Okay, part B in this one was, if you heat a gas at constant pressure, the volume will increase. Okay, now this is all normal. Now I will make a statement that starts out correct. If you heat a gas at constant pressure, the volume will increase. Sounds correct. So that PV is constant and T doesn't rise. Okay, that wasn't one mistake, that was two. I often insert two mistakes to give you the most chances to figure it out. If constant pressure and volume increases, how can PV be constant? That's ridiculous. Now, I also said that when you expand the gas by adding heat, it still gets hot. Remember, that was the second law. You can't turn all heat to work. The gas doesn't expand to absorb all the heat. It still gets hot. So two statements that were incorrect. Okay, part C. Part C. This was the compression factor for perfect gas is 1. That's correct. The compression factor is less than 1 liter when you derive it from PV equals nRT. Two errors. One, compression factors have no units. Why? It's the answer to number 4 in the unit section. Again, question answers to other questions hidden in questions. So when I did that, again, when I said the compression factor is a liter, I'm trying to get you to remember things about units. Also, the compression factor is less than 1 when you derive it from PV equals nRT. That's the perfect gas law. If it's a perfect gas, the compression factor is 1. Two errors in one statement. Giving you, again, that's something to look for. I do it more often than not, or about, well, in this case, about half the time. So that should help you on true and false. Let's see. Okay, other mistakes. Let's take number 6. Okay, we got just a few minutes. Number 6. Okay, number 6 was, just really, hold on. All right, if you want to leave, then leave. All right, so number 6 was the compression factor where it was P over P naught. Here's what a lot of you did. You derived the compression factor from the Van der Waals equation. You derived it. Now, I never said to derive it. I'm looking at the thing. It doesn't say to derive it. You just decided to go to home base. You memorize it, or is it in your calculator? And if it was, you screwed yourself. I told you not to do that. Not because it is cheating. If I see that, I have to bust you, all right? But I don't really care that much because you're going to screw yourself, because that's what some of you did. You just wrote down the derivation. And that has nothing to do with the question. How do you get out of that trap? I gave you numbers. What's Z for a perfect gas? Let's make it steam, which you had the Van der Waals equation, 1 liter at 100 degrees C. Why am I giving you numbers if I expect you to derive something? That doesn't make sense. If I give you numbers, it's a calculator question. Also, listen to me. At the beginning of the test, I said it was a calculator question. So most of you who missed that, that's what you did wrong. If you did the derivation wrong, you used A in bars, but you used 8.314 for the gas constant. That doesn't work. 8.314 is for pascals, not atmospheres. So if you missed it, that's where you screwed up. Number 8 was convert PI over PF, TF over TI. Okay, this was to convert this into a function of temperature and pressure, in which case you just had to insert, PV equals nRT into one side or the other. Now, a lot of you, if you missed this one, you derived this expression from the beginning. Why? No, I'm not going to do that. That's not what the question said. So, a lot of you who missed, all of you who missed this is basically what you did. Number 2, the answer was in the cheat sheet, right? It was one of the expressions I derived earlier. That was done on purpose, right? Again, it was a hidden answer, and it was done in such a way that when I give answers like in this way, when I give answers in this way, by having the actual expression in the cheat sheet, it's been factored. So I make you work, I'm giving you the answer, but I'm going to make you work a little harder to figure out that I gave you the answer. So when you did the derivation, you can just do it in 1 or 2 steps and stop and not simplify it. But if you do simplify it, you get the answer in the cheat sheet, and that's how you know you're right. Again, cheat date, not easy. All right, so we count that. That's how I do it. And I don't have much to say for anything else, so let me give you your test. And I'm going to start with L's in the middle. I'm also returning your unpicked up homeworks.
It actually I have, that's my parents. Oh, but we're never
You're amazing. You're amazing at
I'm not even going to use it. I'm not even going to use it. I didn't even use it on the previous. So it's an original box. Perfect. The only reason why I got the package was because it was going to lower the price of the internet. All right. Thank you.
Oh, are you kidding?
I'm gonna count in school. Just think. You never know. I did pretty good though. I did good. I just did it perfect.
Wait, what are you looking for?
The homework section.
Oh, wait, I got your last name. Yeah, yeah. Oh, wait, I haven't. You got computer, and I got four. So you did number 1.
Yeah, I knew it.
I don't want to. There we go.
Hey, okay, this, we're cool. We're good now.
Yay! 27.5. It was up there.
Oh, I should.
This makes up for my
I don't know if you want to